Hi. So, good morning, everyone. Today, I will walk you through the foundational framework leading up to the Wigner functional theory in quantum optics. We will cover basically the spatiotemporal quadrature states, functional integration tools, and end with fixed spectrum Fock states. So first, let me walk you through the motivation behind this. So we all know that like quantum information technologies offer various advantages in secure communication, precise measurements, but quantum states are fragile and easily can be disturbed. So to enhance the security and capacity, uh, we have to use systems which often use higher dimensional Hilbert space, such as like spatial photon modes. These things offer more information encoding possibilities, but they also suffer from losses and noise, especially from in multi-photon systems. Uh, Traditionally, these systems analysis are very difficult and can be very complex. So some methods are modeled and used using discrete spatial modes, which work well for Gaussian states, but they are not easy to scale. Uh, One promising alternative is to use phase space methods, like the Moyal formulation for quantum mechanics. These in this formulation, the states are the states are represented as functions on phase space. This formalism also allows us to use tools like the Wigner distribution to describe the quantum systems more intuitively. However, incorporating spatial and particle number degrees of freedom in this formulation can be a little bit of challenge. So some recent works and publications has been done on these things, which have tried to unify these degrees of freedom into a single comprehensive Hilbert space. So we have reviewed a journal paper which tries to build up on this idea and fully develop the functional phase space formalism for quantum optics. So our primary aim after reading this paper is to understand how to extend the standard Wigner distribution to a Wigner functional that includes both spatiotemporal and particle number degrees of freedom, and show how quantum optical states and operators can be analyzed using this framework. Also, to demonstrate practical use cases, including like Wigner functionals for various well-known quantum states that will be discussed by my friends later in this part. So first, let us walk through the basic background that is needed for the Wigner functional theory. So we start with the quadrature operators. Here it is denoted by QK and PK, which are analogous to position and momentum operators in field theory. Their eigenvalues equations are given by this, and where the K is the 3D wave vector and S denotes the spin or the polarization modes. So these operators can be constructed, or so we can call decomposed into ladder operators, like in equation 2. And these ladder operators also, these ladder operators we all know from quantum optics that obey certain commutation relations. And so we want to see if these commutation relations we already know from quantum optics is satisfied or not. So in order to do that, we take the help of quantum field theory. From quantum field theory, for bosonic photon states, the electromagnetic field operator can be written like this. And the electromagnetic field operator uh, satisfies the with the commutation relation with the conjugate momentum density operator, like this, and where g mu nu is oh, first of all, I would like to address that we have used this notation here for the four vectors satisfying the gauge constraints. And after that we have did some calculations, and found out that these two operators satisfy this commutation relation. And the real valued eigenfunctions, PS and QS, belongs to the Hilbert space, meaning that they form a complete basis, and there are infinite many eigenvalues. So the choice is not unique, but QS and PS globally represents Q and P states, not just for the individual K states. Therefore, these eigenvectors depend on the eigenvalues, not the wave vectors in infinite dimensional Hilbert space. So after that, we have also seen in quantum optics that the vacuum state is a state that has no excitation. So the definition of vacuum state excitation is written like this: that the A operator acting on a vacuum state gives us zero, and these two relations are also satisfied. Now, in order to make the calculations more efficient, we will define some operators, AQ, AP, and AR dagger, like this, where the D bar K is defined like D3K divided by omega 2 pi Q, where the last one, the AR, is called the pair creation operators. This acts like the squeezing like transformation that ensures correct normalization. Uh, Also, the eigenstate of quadrature operators should be a Gaussian weighted exponential. We already know. So these Gaussian weighted exponential can be written like these equations, where the double mod q square, the definition is like this. For any function f, the definition is like this, where f belongs to R cube Hilbert space. And also, the normalization in the normalization constant, we have omega that is defined like integration delta 0 at d3k. This is called the countable limit infinite volume factor, which represent the cardinality of a countably infinite set. Now we also want to see that the orthogonality and completeness relation that this quadrature operators satisfy. Uh, Excuse me. So first of all, these eigenstates form an orthonormal and complete functional basis. The inner product of Q and Q prime and P and P prime can be written like this, where 2 pi to the power omega is the normalization factor, and this prefactor comes due to the Fourier transform, because we already know that Q and P are Fourier conjugate, acts as a Fourier conjugate to each other. And where the here the delta is the direct delta functional, and omega we have already discussed. This is the cardinality of accountably infinite degrees of freedom. It captures the infinite volume limit and plays an important role in normalization also. Uh, and after that, since they form a complete basis, the spatial temporal quadrature states can also satisfy the completeness relation like in this equation. Here to note is that that d0 p and the dq, these are defined like this, and this is the so-called functional measure over all possible quadrature functions. Now we want to see like until now we have described our expressions in terms of integrals. This is a bit inconvenient, so we want to use a simpler notation for this contraction. uh, in the previous section, the functional integrals can be typically be evaluated when the integrand takes only Gaussian form. So in this case, we want to simplify that. We introduce something called a diamond contraction scheme, where inner product between two functions or their integral over all possible wave vectors can be written like this. This is the integration form, and after the diamond contraction, this can be written like this. Now, when the kernels are also involved, here is the kernel that is written like k vector and k prime vector. The relation can be written like this one in equation 14. And also, where the kernel is not involved, when only the diagonal function is involved, this equation does not hold, and this imposes an inequality with this relation. One example for both being the first one's example can be a 2-point correlation function in quantum optics, and for the second one, the inequality one example can be the Feynman propagator. Now we want to define the Fourier integrals that can be helpful during our next discussion. We already know that the overlap of two quadratures of or the kernel of Fourier transform can be written like this. From equation we have already seen in equation 12 this relation, and using this relation we have got P state and Q state can be written like this. That is simply the Fourier transform, and this is called the functional Fourier transform between the quadrature bases. So now the new position representations of momentum operator and momentum representation of position operator is given by functional derivative, which action can be shown like this. Now using this equation and the definition of the quadrature operators, we can calculate that the operation of quadrature operators on like in order to find the representation, we can act the P operator on the Q state and Q operator on the P state, and we get a result like this. And after that, we can represent from equation 19 the P and the Q operator like this. With this formalism also, we can also define the shift operators and their actions like this one. Here we can notice that there is a shift of Q0 from Q, and that is mediated by the T operator here. Also, we will discuss the integrals for direct delta function. We study integrals of the form in this way. Delta Q1 minus Q2 can be written like this, so I already know. And similarly for P states, we can write like this. And now let us define the alpha operator as the linear combination. Sorry, not the linear combination, but it can be defined as a combination of Q and P operators. And this can also serve as a parametric function. And in order to calculate this, the Dirac delta functional, we have to calculate this first. And this expression results in this one here, integration Q0 P minus Q P0 del K. And after that, we put this expression into our equation 22, and that will result in 2 pi omega delta alpha 0, where delta 0 alpha is defined as delta Q delta 0 P, and delta alpha 0 is defined as delta Q0 and delta P0. This sets us up to the discussion of Fock states and coherent states in the functional formalism. First of all, we want to discuss the fixed spectrum Fock states. The fixed spectrum Fock states are defined by this expression NF and 1 divided by root over n factorial alpha f dagger n with a vacuum state acting on vacuum state, where alpha f dagger is defined like this, where f is the Fourier domain wave function, and it is defined like this. And let us check if the simple commutation relation we already know from quantum optics, that is this one is already valid, this one should be 1. So let us see if that is 4. So we have done the calculation here, we have set up the integrals, and we have done the integration, and after that we can see that this results in 1. So our formalism seems to be correct up until now. So it is valid. And now the action of annihilation operator on fixed spectrum Fock states are defined like this. And these states are eigenstates of the so these states are eigenstates of the number operator, and the number operator is defined like this one we already know. And from equation 27, using the number operator, we can see that this one satisfies this equation. Sorry for the typing mistake here. This will be n only. And the takeaway from this section is that uh, this the A operators obey the canonical bosonic commutation rule, and the action of we have seen the action of annihilation operator, and we can conclude that these states are eigenstates of the number operator, and this builds the connection with the observable particle counts in quantum optics. So after that, we have we want to see for fixed spectrum coherent states after Fock states. The fixed spectrum coherent states are defined like this, and so the fixed spectrum coherent states are uh, eigenstates of the annihilation operator and the eigenvalue function of the alpha. That is complex spectral function. So they represent quantum states with well-defined spectral distributions, and they do not explicitly depend on the wave vector k. These states are widely used in quantum optics and condensed matter theory, particularly in the green function calculations. Here, the subscript F describes the parameterization by a fixed spectrum rather than labeling a specific functions. So, during class also, our class also, the fixed spectrum coherence states, there we have associated the displacement operator. In this case also, the displacement operator can be defined like this, but we have used the diamond contraction here, and after that we will see the inner product between them. We have taken two inner product of two coherent states, and we have calculated it, and we see that the coherent state inner product after calculating the inner product between two coherent states are exponential minus half alpha square minus half beta square, and inner product between alpha and beta. So if we set the beta to be 0, that is the vacuum state, we can see that the inner product between the vacuum state and alpha is simply exponential of minus half alpha square. Also, one thing to note is that this does not result in 1. So these are not orthogonal quantum states. So, but although they are not orthogonal, these fixed spectrum coherent states can be resolved to identity with some simple integral calculations in the Bragg-Band representation, and the in completeness relation simply reads like this. And Finally, we see that the quadrature representation of coherent state can be written like this. This comes from the equation we have derived, we have defined earlier, like it here. We have defined AQ, AP, and AR, and we want to see what are their actions on the coherent states. We have acted on the two coherent states, the AQ and the AR operator, and we have got the results like this. And we have taken the inner product between the coherent state and the Q, and we have got this result. So where alpha 0 is the complex valued parameter function, and these results will be handy later in the later part of our discussion. So I will hand over to Mongol to discuss with the Wigner functional theory with the help of this formalism. So he will continue now.
Hello. Hello, my name is Mangal. I'll discuss the part Wigner functional theory and how this theory helps us to extract the information about the system. First, let us talk about the what is Wigner function. It's sometimes called the Cauchy probability distribution. Why it is Cauchy? Because it can also take the negative value. That's why it is Cauchy. And this was first introduced by Wigner in 1932. The main aim of this Wigner function theory is to make a link between the quantum theory and the statistical phase space theory. Okay, the definition of the Wigner function is given by this, where x and p are momentum and position. Okay, but it can be any two conjugate variable pair. And this is for a pure state. But if we have a mixed state, in general, for a mixed state, the Wigner function is given by this equation with the density matrix rho. And if we put rho for a pure state by this equals this, and if we put into 2, we'll easily get the equation number 1. And now the problem in the Wigner function is that it only represent the particle degree of freedom, but Wigner function is more advanced than Wigner function because it also represent the position and temporal degree of freedom. So we'll discuss this Wigner formalism in the context of quantum optics, and but for now we'll neglect the spin index, but once necessary, someone also put the spin index into the theory. The definition of the Wigner function is given by this equation. This is just a definition. This is a definition for any operator in the Hilbert space. For any in any operator in the Hilbert space, it might include the spin, time, and space also. And the square bracket indicates that it's a functional, not a function. Means the integration value not only depend on the value of the Q and P, but also depend on the functional form of the Q and P. That's why it is functional. And Q and P, the quadrature state for the quantum optics case, and they are real valued, and we can combine Q and P in alpha. And in that case, the Wigner function is represented by W of alpha. Now, density matrix. The element of the density matrix for a state is given by the density functional, and this is the definition. And for a pure state, we know we can put psi, h psi, and bra psi in middle, and then we get this psi and psi star. This is the representation of the density functional. Now Wheel transformation. What is Wheel transformation? Wheel transformation is the inverse transformation of the Wigner. Means it transforms the phase space probability into quantum mechanical operator in Hilbert space. Okay, and now define these two in the first equation: q plus half x and q minus half x by two variable q double dash and q dash. And if we put, we'll get the inverse transformation like the Fourier transform, the Wigner transformation of this Wigner function, and we'll get the density operator. So from this, we can convert the Wigner function into the density operator and density operator into Wigner function. And because the density operator, we can extract the information about the system from the density operator. That's why we need it. And the density matrix is given by this, the sum over all component. And if we put this row from this equation, so this is the form of the density matrix. And we have to check that we know for a pure state, the trace of the density matrix should be on. So let's check it. If we can find the trace of the density matrix, like sandwich between Q and Q, then this inner product is nothing but the x by 2, and this inner product is x by 2. And we know that from the symmetric of the delta function, they are same, so we can write delta x by 2. And this is only survive when x is equal to 0. Okay, so we put the x equal to 0, and the x contribution vanish from the integration, and we can combine q and v that into alpha, and this as d0 alpha, and this is the normalization condition for the Wigner distribution, as this is a probability distribution, and then it should be normalized. So we see that the trace of rho is equal to 1. Now the expectation value we can calculate from the density matrix, as we know that the expectation value of the operator is sum over all contribution from all state. So rho I, and we can impose the identity operator in between them j, then we will get ij, and then this rho I and inner product of j and I, we can retain as the matrix element of rho, and this is the trace of rho and o. So we can extract the information like the expectation value of the O operator by finding the trace of rho and O. And this is the integral form of this from this equation. This is the integral form of this expectation value, where W rho is the Wigner function corresponding to rho operator, and Q O W is the Wigner function corresponding to rho O operator. And that is the definition of Wigner function. Now, what is star product? Star product, we have, let's say we have two operators A and B, okay, and the Wigner functional from them are W and WB, and the star product gives us the information, gives us the Wigner function for the product operator like A and B. So it's given by this definition, W of AB, Q and P is given by this equation. From this equation we can calculate the Wigner function for the product operator. That's all. And now Saurabh will present the rest of the rest part.
So hello, myself Sadev, and I am talking about characteristic functions. So the density operator in coherent basis can be written as this. Rho cap is basically integration of d square alpha p alpha, now the product of this alpha. So there the p alpha is basically global Sudarshan p function, which represent the quantum state in the classical probability distribution over the coherent state. So this is basically a characteristic function that is the Fourier transform of the displacement of operator and sorry, Wigner function operator, and you can see that there will displacement operator and the chi is written as the trace of the d xi of rho cap, and this then rho cap is the density matrix operator. So and d is the displacement operator. So what is the displacement of the state from the mean position, and this wheel operator can be written is defined as e to the power xt, and this omega chi, and you can see that this is basically x is here is the H space quadrature for a single mode system. So you can write the symplectic matrix for a single mode this by this matrix, and the vector the phase space vector by alpha and beta, and you put that in that equation, then you can find that this is basically the I beta x cap and alpha p cap in the quadrature operator, and you can find that this is the annihilation operator and the creation operator in terms of the annihilation operator and the creation operator, where we define that this n is basically the linear combination of alpha and I beta by root 2. Okay? Then I am going to the characteristic function. So what is the characteristic function can be written as this. This is the basically you simplify this, and you write this in terms of a cap and a cap dagger, and after that you find that that characteristic function can be written as trace of this thing, and so if we put the a cap and the a in the equation, and you take that inner product, then you can find that this Wigner function is basically the characteristic function is basically the Fourier transform of the Wigner function. So here dq and d not q. So dq is the measure of the q in the coordinate basis, and d not p is in the momentum basis. So the Wigner function can be written as this in this inverse transformation, and where w the Wigner function of for the displacement operator, you can write this in terms of e to the power alpha star and alpha naught, and minus the alpha naught alpha star, alpha. So now we are talking about marginal probability. So what is the WQP? WQP is the basically functional. So W depend on the Q and P, the quadrature, and you can see that there is basically these are functional. So you can write in terms of this, and uh, as the quasi probability distribution over the function phase space, the Wigner functional of state doesn't satisfy a two probability density, because there is a negative also, the probability will can be negative. So this probability, if we integrate this probability over the P and Q, then we can find that this is basically shows that the um, d naught p over integration of omega p q phi. This is basically given by the this equation, and there you can see that this is the delta function, and putting into the equation, in this equation we can find that this is basically right written in the position coordinator, means the density matrix can be expand in the position coordinator. If we marginalize the function over p, then we will find the probability of the coordinator basis, what I am saying that. And if we integrate over q, then you can see that there, if we insert the identity p1 and p1, and the outer product of p2 and p2, then their d naught is basically d naught p1 p2 is the basically differential. So after simplifying that, we can find that this is basically the major probability in the p space. So now Arijit will discuss for the next lecture.
So, hello everyone, myself Orjit Maji. I am going to derive the Wigner function of coherent state, and I have also plotted them in Python. So, after deriving the coherent state, Wigner function of coherent state, then I am going to plot them in show the plot in Python. Can you see the presentation? Hello, anyone confirm, please? Okay. So first of all, the characteristic function can be written as chi of theta equal to trace of rho e to the power eta a dagger cap minus eta star a cap. This is the characteristic function. We can written this way, and for coherent state, the rho is the density matrix, can be written as alpha 0 outer product for alpha 0. Alpha 0 is the coherent state, and this is also a pure state. And now I am going to derive the Wigner function of the coherent state, and it could be written as omega of alpha equal to 1 by pi square. This is a normalization constant e to the power eta star alpha minus eta alpha star chi of s. This is the characteristic function, and d2 eta. This is the integral. Now we know the some basic property of density operator and the characteristic function. And this way we can write this as e to the power n star alpha minus eta alpha star, and alpha 0. This is the displacement operator d cap n, and alpha 0 d2 eta n. Now there is some basic property of displacement operator. I am going to write down them, and for time constant I cannot derive them properly. if we operate the displacement operator d cap of alpha 0, then we get on vacuum state we get the coherent state alpha 0, and there is some also property of the density operator. This could be written as this way. This is the some property of displacement operator, and this could be proved very easily. And now we can read. We can there is also some other property. They could be written as this way. And this could be simplified as to the power minus alpha square by 2 e to we cannot go this way. E to the power eta star alpha minus alpha 0 minus eta alpha minus alpha 0 star e to the power minus eta square by 2 d2 eta. And finally, we know that eta is a complex number, so it could be written as a real and imaginary part. And alpha minus alpha, both alpha and alpha 0 are imaginary a complex number, so it also have real and imaginary part. So both of them are written as So finally, we will get, we have to use the standard equation, standard integral. Square minus half of a x square plus I j of x. This would be written as 2 pi by a whole to the power half e to the power minus j square by 2a. And after all, using all this equation, we will finally get the Wigner function of the coherent state as 2 by pi and 2 by pi e to the power minus 2 alpha minus alpha 0 the whole square. This is our final equation. This is the Wigner function of coherent state. Now I am going to show the plot in Python. Here is the Wigner function of coherent state as alpha equal to 1.2 minus 2.2 j. As we know that alpha 0 is a complex number, so it has real and imaginary part. For alpha equal to this number, the Wigner function will look like that. We can change here the parameter. If we do that, if we change it, sorry for this moment, it's not working. But I have put the whole code in our report. We can check it later. And for this alpha 0 value, the coherent state will look like that. Now Anmesh will take over for the final part.
Okay, so hi everyone. I'm Onimus, and in my part of the presentation, I will try to give you an idea that how the Wigner function representation of one of the most crucial operator, named displacement operator in terms of studying theoretical quantum optics, is really how does it look like and how should we approach the problem. And apart from that, I will also try to give you an understanding of how time dependence in the Wigner function comes in later part of my presentation. Okay, so the screen is visible, right? Hello.
Yeah, screen is visible.
Yeah, sure. Okay, so in my part of the presentation, let's see. Okay, so the displacement operator, as we already have discussed, is kind of look like exponential of alpha or diamond product with alpha dagger, a dagger minus alpha star times diamond product of a cap. Now we are using a Baker-Campbell as Baker-Campbell-Hausdorff formula that exponential of the addition of two operators is essentially exponential of minus half of commutation of the two operators times exponential of the first operator times exponential of the second operator. Now, this is an approximate relation because we have taken, we have assumed that the commutation of x with commutation of x and y and commutation of y with commutation of x and y both are 0. So if we put those values and if you calculate this commutation relation, we get that it is nothing but mod of alpha square. So now keep in mind that we have taken two strokes, two horizontal strokes. That means we are taking modulus of a function, not a complex parameter. So this is the thing I want to kind of remind you. So the displacement operator is looks like if you put these values, simple. If you just put these values, you get d of alpha naught is equals to exponential of minus half mod alpha naught square times exponential of alpha diamond product with a cap times exponential of minus alpha prime diamond product of a with a. Now let's try to compute how does it look with given the overlap with the coherent state. So what we are interested in is trying to calculate this element. So now if I apply a d of alpha 0 at alpha 2, what you get is alpha 1 times alpha 2 plus alpha 0 because this is the job of the displacement operator. Now remember, if we have two coherent states and we are taking net product, from earlier discussion we get to know that the expression looks like this. Now what we will do, we will put alpha equals to alpha 1 and beta equals to alpha 2 plus alpha naught. And by putting this, we get this expression. Now, if you try to just a bit simplify, and it kind of looks like this. So now we have the expression from the earlier discussion that Wigner function of an operator is essentially some normalization constant times a big exponential time the matrix element, the alpha 1, alpha 2 element of the matrix, of which I am trying to find out the Wigner functional representation times uh, and the total integral will be over alpha 1 and alpha 2. Now, if we try to plug this in, what we have is n naught, we have the same value and this thing. And now the interesting part is that we know this, what this looks like. So we put this value, we get a big exponential inside the exponent, we get a big expression, right? Now, what we want to do, we want to integrate out all the alpha 1 and alpha 2 dependence. Now, if I want to integrate out the alpha 1 and alpha 2 dependence, okay, so I think it would be easier to share the screen if I can. Okay, the screen is visible, right? The iPad screen is visible, right? Anyone let me know. Hello? Hello?
Yes, it is visible.
Okay, sure. Okay, so all the terms that we have in the exponential, we have taken out all the terms which only have alpha 1 and alpha 2 because that's what we are kind of interested in, right? We are trying to integrate out alpha 1 and alpha 2. So what we have is these are the out of 10 terms, we have these are the 8 terms that have alpha 1 and alpha 2 dependence. Okay, and now we know the famous Gaussian integral that we have. If we have some column matrix times a square matrix times a column again, then we have this kind of structure. Then we have a column matrix times a matrix again, and we are integrating out it. We get exponentials of this zeta star. We have exponential zeta star k inverse zeta divided by the determinant of the matrix that is present over here. And if you look carefully, we have the exact same structure over here as well. We can represent this S in this matrix form as well, where your simple alpha is essentially alpha 1, alpha 2, which sits over there. And if you compare it, this is essentially our K, and the xi component is essentially the multiplication of these two guys, and the zeta is essentially multiplication of these two guys. Okay, now we got to know what is our k is, what our zeta is, what our xi is. Now we should be able to calculate this thing, right? Okay, if we want to do this thing, let's see. So as we discussed earlier, we have alpha, we have zeta, we have xi, and we have k. Now I created I wrote a simple Python programming that do that exponential of zeta star k inverse I, and if you run the code, and what it does is it gives you the value of the integral. So the value of the integral is gives you this. Why the bar means essentially the complex conjugate. Okay, so this looks like this, and if you think about it carefully, earlier we have two expressions, two elements out of. So we said that we have 10, 10 terms over here, out of which 8 have alpha and alpha 2 dependence. Those who are not alpha dependent, not dependent on alpha, are these two terms, alpha 0 and alpha. And if you think about it carefully, these are appearing over here as well, and they will cut themselves exactly, they will cancel themselves. So after all that, the Wigner functional representation of the displacement operator, starting at alpha 0, with a displacement of alpha, it looks like exponential of alpha star alpha naught minus alpha naught star alpha. Okay, now if you want to calculate, let's say I want a general representation of a function, general representation of an operator. How should I go about it? Okay, so let's say our general state is a density matrix I, a density matrix rho, and if we want to calculate this, we already have our expression that we have already discussed. W of ABC of alpha, we have this big expression. Now the things to note is that we know exactly what the W of now if you compare it with this, we can say that, okay, so our A is essentially a displacement operator, C is essentially a displacement operator again of dagger. And if you put, we already know how those Wigner representation of those operator looks like. We put them and we merge the exponentials, and we also left with exponential of this exponential this WB of alpha 0, essentially W rho of alpha A with the integration. And if you do the integration, the thing to note that alpha B has no quadratic dependence. So what we essentially have is simply Dirac delta. If we integrate it, we put the Dirac delta and simply integrate it out. We get simply omega, we simply get W rho of it's like alpha minus alpha naught. Okay, so this is essentially you can represent any operator in terms of this. Some important thing to note is that, okay, so there are some misleading things that may be going on that we are interchangeably using Wigner function and Wigner functional. They are really not same. Wigner function is basically something that only incorporates the particle number degrees of freedom, while Wigner function takes care of both particle number of degrees of freedom as well as the spatiotemporal degrees of freedom as well. Okay, for example, if you take a coherent state, the spectrum, the Wigner function look like exponential of simple this, but the Wigner function is essentially this. Two things where it differs is that this is essentially alpha minus alpha naught is essentially a complex parameter, a complex number. You are taking mod of it. But in case of Wigner functional, it's alpha minus alpha naught is a complex function. You are taking mod of it. So they is not really same. And one thing you can notice is that the normalization constant is different. For the former case, it's really a finite number. But if you take a continuum limit, then essentially the 2 to the power omega is essentially associated with the cardinality of the space set, and that can be countable infinity for continuum limit. Now, apart from this, let's try to see it's a good idea to try to see the time dependence of doing a function, and if that exactly matches with our normal understanding of Schrodinger equation. For let's say take a simple example of free particle, and the particle starts at t equals to 0 at let's say at origin with a Gaussian form, and I let it evolve with the energy available. So this is the time dependence that we have, and the essential time scale is tau, which is essentially the time scale of the problem, that is m by 2h cut a. Simply calculate the Wigner function here, not a functional, we are calculating with a function. So it's the psi star psi with the different arguments. You put it and it gets a simple integration. What do you have? This time dependence of the function that we have. Now what I did, I just ran a code that shows the time dependence, and if I run the code, okay, if I run the code, what I have is, let's say at t equals to 0, what we have earlier expected, we started with a Gaussian at x and p, we exactly have that. Now if I increase the time, a little bit. What we are seeing that at, let's say, t equals to 5, the particle is essentially spread out. The Wigner function probability is essentially spread out in x and kind of get localized on some specific values of p. If I keep on doing this, and what we are seeing is x, the probability at a, around the probability of finding the particle in minus x to minus infinity to plus infinity is kind of become uniform, and it's taking some specific value some of momentum. So that's what we are expecting, right? If we are try to evolve a free particle in a free potential, it's in a v equals to 0 potential, it will essentially take a plane wave kind of equation. So the wave function will be equiprobable in all of the x values, and it will take some momentum based on the initial condition. So this is our structure that we are kind of getting, and that is all from our side, and this is all we have done in our project on Wigner functional technique in quantum optics. Thank you.
Okay, so I guess everyone is finished, right? Okay, so let us end this video now. Thank you to all the group members, and let me end this meeting, right? Can I end this meeting? Okay.
Yeah.
Sure.